So good morning again, everyone. Uh, Today we should continue on chapter 3, right? So last week we have looked at the development flow of how to develop microprocessor project, and we have looked at data representation, uh, where we look at how we represent or use the data in the microprocessor. And we have looked most of the instruction set already, and today we will continue on the the last group of the instruction set, which is the program controller flow control. And we will also look at this how to write the code, the program, the complete program based on what we have learned here, instruction set. We will use what we have learned in here to write the complete code here. And we will look also the equivalent C program for the assembly code. So last week, these are the instruction groups that we have learned. Moving data within the processor, the internal register. We have done this already, and we have learned also how to access the memory, how to load the data from the memory, and how to store data to the memory. And we also look at arithmetic operation, the add operation, the sub operation, the multiplication, the division, and also the logic operation, the shift and rotate operation. And today we will look at program flow control. Right. So here is the program flow control. So program flow control is a very important features in microprocessor programming or computer programming, where normally when we write the program, we not always run the program in a sequence step by step. Sometimes we want to branch, we call it branch, or we want to go to other location other than the normal flow based on some conditions. All right. For example, at some point we may want to test whether this condition is true or not. If true, what to do. If not true, what to do. So that will be in this group of instruction, the decision and conditional branches instruction. So that the microprocessor will know that by looking at this status flag, status bit, the N, Z, V, and C. So for example, if we compare a number, for example, A compare B, compare in computer is actually to minus. For example, we want to compare A and B. Actually, what the computer do is to minus A minus B. Just like we did in the designing of the comparator in data design, where if we want to compare the number, we use subtraction, A minus B. So if the result is positive, so we know exactly that A is greater than B. If the result is negative, we know that the A is less than B. And if the result is equal, result is 0, means that A equal to B. So that will can be known by the microprocessor by looking at this bit. For example, if n equal to 1, means that the result from the compare operation is negative. If n equal to 0, means that the result is positive. If z equal to 1, means that the result is 0. If v equal to 1, we have overflow. If c equal to 1, we have carry. right? So we can use this status flag to for the branching operation. As we know, in our microcontroller processor, we have another flag called the Q flag, and the branch operation is not using this Q flag, yeah, only these four flags, yeah. Right, so these are the branch instruction that we can use in our program, and this is of course the instruction also in microprocessor. For example, EQ, so our instruction will have B in front and branch, so the full instruction is BEQ. So what is BEQ? BEQ is means that we branch if the condition is equal, means that if we compare before the we check whether it is equal or not, we need to compare. So if it's equal, so we will branch, do the branch, or jump to the new location. And the flag that this instruction will check is Z flag. All right, so if equal, of course, when the result is equal to 0, right, so Z is set and we jump or we branch. And we have also NE or BNE, branch if not equal. So if not equal to 0, we branch. We have branch if carry set or CS, or we can use also HS. This should be the same. All right, carry set or unsigned higher or same. We have also carry jump or branch if carry is clear. So means that looking at C flag. Yeah. And we can also jump if minus, jump if plus or positive, branch if overflow, no overflow, higher, unsigned higher, BHI. So for example, we compare an unsigned number, two unsigned number. So we can use BHI if we branch when the number that we compare, for example, A and B. So if A is higher than B, so we branch. This is unsigned lower, BLS. GE, sign, so this is for sign. For example, if sign number, we can use BGE, greater than or equal. BLT is less than, BGT is greater than. And we also have LE, sign less or equal. And we also have the last one, BAL or just B, right? This is always branch, no condition, unconditional. Means that if we have this instruction BAL in our program, your program will need to branch, no matter what is the condition. So this is unconditional branch. So sometimes we need this also. We will see later on when we write the program later. Okay, so this one we will look at the example later on. Now we want to write the assembly program, the program that we use uh, to instruct the microprocessor to do the job that we want to do. We call it the program, right? So the microprocessor will run the assembly language, yeah. So the assembly language is unique to the microprocessor. For example, if you use ARM microprocessor, the assembly language, the instruction set that we use is specific to the ARM. If we use Intel microprocessor, the instruction set is specific to the Intel microprocessor. So if you write the program in C or higher level programming language, all right, when you use ARM microprocessor and when you program in C, actually the compiler will convert the program to the ARM instruction set. Yeah? But if you write the program for the Intel microprocessor, so the compiler will compile your program to the Intel instruction set. Okay, so Now we want to learn the instruction set and the assembly language. Why we need to learn assembly language in learning microprocessor? Because this is the most uh, optimized language for the microprocessor, right? So if you can write the assembly program, so you can have the very optimized program and the very fast program for a particular microprocessor. And also, normally if you write the code for uh, OS or the uh, uh, firmware, so to optimize certain part of the task, assembly language is the best solution. Um, but of course, uh, writing a program in assembly language is quite difficult, quite hard, time consuming, because you need to understand the hardware architecture of the microprocessor as compared to C programming, where you don't need to know the hardware architecture, right? Because you are at the higher level of the uh, hierarchy, yeah. So to learn microprocessor, the best way is to know the instruction set and to learn the assembly language of that microprocessor, right? So in this course, we will start programming with learning the assembly language of this microprocessor, the ARM microprocessor, right? So the first thing that you need to know when you want to write the assembly program for the microprocessor is what we call the assembly directive, right? So this assembly directive is not the instruction set. It is a command, assembly command, that is used to control or give command to the compiler, or what we call the assembler, right? Assembler and compiler is the same, yeah. So for example, area, when we write area in our program, this is used to tell the compiler or the assembler that this part of our code or area is for code or data, right? So we can uh, set in the memory, in the microprocessor memory, that certain area is reserved for code or reserved for data. And the next one is EQU or equate. Yeah, so this is used to equate a symbol to a numeric constant. For example, if we have uh, the symbol, right? Uh, Data, for example, equate what? We equate to the constant, to the number. So next time we want to use that constant or number, we can use that symbol instead of number, right? We can see later. Entry, to declare the entry point to the program. DCB, define constant in the byte size. Uh, uh, Half-word and word size. So this is the to allocate the memory location in the memory uh, with content, with predefined content. Later on, we will see. Align, to align data or code to a particular memory boundary. And this is very important also when you write the assembly program. So if you don't have you will have error when you compile your program. So this is to tell the compiler that this is the end of your program, the line, end of the line. So after this uh, is not the program anymore, something like that. Export is to declare a symbol that can be used by a linker. So this is for the linker, right, to resolve symbol references in separate objects and library files. So if you have many library, so Normally we use export to reserve the symbol issue. This is the example of assembly program for the ARM microprocessor. So we can see that this is the assembly directive, yeah, that here. So this is not the instruction. This is not microprocessor instruction set, all right? But this is the command for the uh, assembler or compiler, all right? So for example, we define the area for the code, and this is a read-only area, and this is the body of the code, all right? And this we call the label, all right? This column we call the label. So this label can be any name, but you need to start with alphabet. Okay, and the second column is called the mnemonic, or sometimes we call opcode. And here is the operand, right? So you can have the destination operand, and also you can have the source operand. And here is the command, right? So command is skipped by the compiler, right? Where the compiler will not translate this to machine code, right? This is just for our reference, and this is a good practice to write a comment for your code, yeah? Because if just imagine that if you don't have this and you only have the program, so to understand the program is quite hard, yeah? Especially when you want to give this program or send this program to other people, uh, uh, to your friend, for example. So your friend is need to know what you want to do. So here in the comment you write what you want to do. For example, in this line you want to move 16-bit this to this R2 and so on and so forth, right? So that the program is more readable if you have the comment. And here is how we define the predefine the content of the memory. We will learn later what is meant by this. Yeah. Okay. So here is how we define the data in the memory. So for example, we want to in our program we want to use predefined data in our program. So we can actually predefine that data in the memory. So for example, when we write my data, this is my data, like something here, my data, and dc.b means that my data is in byte size. Yeah, dc is defined constant, b is in size byte. So if I write like this, yeah, so this is the first byte, second byte, third and fourth. So in the memory, it will store like this, yeah. And the address, the microprocessor, the compiler will automatically define the address for you, all right? Because you write this with the code. So this will be somewhere in the memory after your code, right? So here, for example, it is stored in this location in the memory 100, yeah, 10, 11, 12, 13, right? But when you want to write the ASCII character in the your program, yeah, for example, you want to define the word hello in your program, so you can use dcb hello with this code, right? And in the memory, it will be stored like this. So it will not have H in memory. So in your computer, it store the value H in ASCII representation. So this is 48 is ASCII representation for H. Yeah. So when you use the, for example, you can Right, when you look at the ASCII table, for example, here's the ASCII table, right? So when we look at H here, yeah, character H, and it is represented by 48 hexadecimal, yeah, in a digital hardware, right? So this is H, this is E, this is L, this is O. Okay, so when you write this in the computer memory, microprocessor memory, it is stored in this representation. And we can also define the size, the different size of the data. For example, we want to define in half-word size, right? The command is dcw, right? Not dch, half-word, but w, right? 1011. So this is the half-word size, yeah, hexadecimal. So in the memory, we will have 1110. And remember, in ARM microprocessor, the data is stored in the little endian format, yeah, in the memory. So 11 will go first, 11 and 10. And the second word, half word is this 1213. So we have 1213. And if we want to store in word size, or 32-bit, so this is how DCD, right? 1011, 1213. So we will have 13 first in the memory, 121110. Okay, so this is how this is stored in the memory. Okay, we also can use this instruction, LDR R0 my data equal my data. So this is new for you. So last week we learned the LDR, which is the load instruction to load data from memory to the register, right? And last week our load instruction is we have the memory address here in the register, right? So that we can load the data that is pointed by the address here. But here is the new instruction for you. For example, if we have my data and we define the my data in our memory here, okay, and if we write the code like this, R0 equal my data, it will load, the microprocessor will load the address of my data into R0. So for example, in this case, the address of my data is 100. So when I execute this instruction, so what happened is that R0 will have 100, the address, the address will go to this, but if my instruction is like this, I don't have equal sign. So what happened is that I will load, and the instruction is LDRB byte. So I will load the data from the memory to R0, not the address. If this, I will load the address. If this, I will load the data. And what is the data? If I use LDRB, means that this data, this one, because my data is at this location. So I will get 10. And again, this is not instruction set. Actually, this is like the assembler directive. When you write in the kill, it's actually converted to an equivalent instruction. Yeah. So for example, let's try to write this thing in kill. UVision and see what happened when we do that. Okay, let's open this. Okay. Where is it? Okay. So I want to start a new project. Before that, I want to copy this. Okay. So let's have a new project. Okay, and we need to use the assembly. ASM is assembly, so assembly file for the source code. So I want to have this. Okay, let's see. In this case, for example, we have the odd 0 data, and I use this, and the second one is this, and we don't have anything here, just an OP, for example, and here we have this. Okay, my data, correct, and I have n here. Now try to simulate the program. Go to debug. Okay, need to compile first. Okay, no error. Okay, so now I try to run the program, and now where is our data? And in the microprocessor memory, so we can actually move the cursor to here and click here, and we can see that this line LDR R0 is this highlighted. You see, when you move, this is the second one, this is an OP, and they are. So let's see this. When in our program we write like this, but in the actual implementation, this is actually LDR R0 PC. Means that the value in the PC, this is offset, plus with 8, and get the value, or this value actually will go to R0. Okay, because this my data is in where is my data? My data is this actually. This the CW. Our data is 1011, 1110, 1312. All right. So in the memory, so we can see in the memory how to look at the data in the memory. We can go to the memory, and here we can because the data is somewhere here in this location. All right, here. So we can have this starting with 0, 0, 0, 0, 0, 4, 0, 0. Okay, so this is our data 1011, 1011, 1213, 1011, 1213. So this is the data in the memory. Okay, how to know? So this is the address, 408. So this is 400, 401, 02, 03, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, this is 408, 409, 40A, 40B. Okay, so that is the data in the memory. So now, when we execute this instruction, what happens is that it will move the memory address of the my data, which is this 408, to the R0. So let's run the program so that we can see. So we run till here. So see, 408 will go to R0, right? And when we run this one, so my data will go to R0, and this is LDR. We should have LDRB, right? Cancel again. Cancel. The instruction is LDRB. Okay. Right, so this is memory. And let's run until this line. And it's go to R0 also. No, I don't want this. Go to R1, right? So that we can see again. So when I run the program, memory, now the in this program, okay, our data is in 0, 4, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9A. All right, that's why we have 40A in R0 when we use this instruction. And when we load my data to R1, so my data is 10, go to R1. Yeah, 10, right? Okay, that is the meaning of this. Okay, this is important for you to know how the data is stored, how we write the program to predefine the data, and how to locate the data in the memory. I want you to understand this, right? So if you have any question, better you ask now, or if you want me to repeat, yeah, what is mean by this thing, so maybe I can repeat. So any question? Okay, what if we have something like this? Anyone can answer. What if we have something like this? LDR, R0, my data. Okay, so let's see. LDRW. We don't have LDRW, right? LDRH. Now, now is our program is like this. So what will be in R0 when I execute this program, this instruction, the first line. So again, we need to check uh, where is our data, my data in the memory, and we know that my data is this, all right. But we need to know where is in the exact location in the memory, the address of my data. So how to know? You need to here go to DCB. Yeah, or you can this, yeah. So this is your the address 4040A, right? DC in this assembly window it will always show DCW, yeah, no DCB. But in our program we can have the uh, flexibility to use DCB, DCW, or DCD. But in at this assembly window, it will always DCW, right? In this case, our data will be at the 40A, right? So when we run or execute this instruction, the address, remember if we have the equal sign here, means that the address of my data will go to R0. So when I run this, run, right? So it will have 40A in my R0, in R0 register, right? The address. So here 40A, and in the memory we can see where is our data. 10111213 is here actually. How do we know this is our data? So again, we need to look at the address. So the address in the memory view in kill, it will display like this. It will not display all the addresses. 4000401, no. It will display like this, where here is 400, 40F, 40E. But we need to know that this is actually 400, and this byte is actually located at 401. This is 402, 3, 4, 5, 6, 7, 8, 9. This is 409. This is 40A. This is 40B, C, D, right, in the memory. So if we draw, yeah, this in the memory, it actually looks like this. Uh, so this is our memory, and remember the memory is always 8-bit in size for one location, right? So the first address will be 400, and the size is always 8-bit. And this is the data inside here is this 0, 3. So this should be 0, 3. And this should be 48, the next one, 48 in the next location, which is actually this one, 401. This one will be 402, and the data is BF, and so on until we have here is 0, 0, 0, 0, 0, 4, 0A, which is this one, 1, 0, 1, 0, and the next one will be 0, 0, 0, 0, 0, 4, 0B, which is the 1, 1, 1, 1, and the next one is 1, 2, 1, 1, 3. Right? So this is how the memory is organized in ARM microprocessor. And before this is actually the machine code, right? For example, 400. Yeah, we can look at this. 400 is actually 4803. 4803 here is actually for this instruction LDR. Yeah, and this is the next instruction, and so on and so forth. Right? So now, what is the answer for this LDR? Yeah, LDR H, R1 my data. What should be in R1? So we have R1, R1, and what should be in R1? So when we anyone want to answer before I give the answer? Who give the answer? Ching Wei Lun, yeah. Ching Wei Lun said the answer is again 0. How many 0? 40, 1110. Are you running the kill? The kill? Oh no, eh? Okay. Is it correct? Anyone have different answer? No? Agree? I think all agree with Ching. Okay. So let's see. Uh, we can run this. Okay. So we can use this step one line or F11. So when you click, and make sure that if you want to use this, you need to bring your cursor to the correct line or instruction that you want to execute. So for this example here, this instruction we want to execute. So make sure that our cursor is here and we click. Yes. So this is the answer. Is it correct? Yes, correct. Yeah, 1110. All right, 1110. So correct. Yeah, good. Okay, so that is how the data is uh, predefined or stored in the memory, and how we use the LDR instruction. Okay, now go to the next. Uh, Before we go here, the program control. Uh, Last week, yeah, when we when we want to move a 32-bit value into a register, for example, we have this in R0, and we want to, for example, want to move 1, 2, 3, 4 hexa decimal number 5, 6, 7, 8, which is 32-bit now, into R0. So what we do is we use MOV W or move wide R0 immediate value, right? This, and we use move top R0, right? Because we don't have any instruction to move immediate data that is 32-bit in size into any register. We just don't have. Because let's see, for example, if you want to move the data, right? Let's say, for example, in the code, you want to move move instruction, any move instruction, R2, like 32-bit data into R2. So when you do this, you will have error, because this immediate data cannot be represented by 0 to 255 shifted left by 0 to 23. So there is no operation, shift operation or other operation, for example, duplicate operation to create this value from an 8-bit data, because the immediate data is 8-bit, only allowed for 8-bit, except this MOVW that we can have 16-bit, but the maximum is still 16-bit. We don't have any instruction to move 32 immediate data into a register in single or using single instruction. We just don't have that. Why? Because remember that this instruction, all right, every instruction here will be encoded into a machine language. And machine language for ARM 32-bit microprocessor, the maximum size is only 32-bit. All right. If you look at, sorry, we cannot debug here because this is wrong. So for example, we change this to 8-bit and we run. And yes, of course, no problem because here is 8-bit. And the assembly language, no, the machine code for each instruction that we use will not more than 32-bit. Maximum is 32-bit. It can be 16-bit. It can be 32-bit. For example, LDR is 16-bit. For hex digit is 16-bit. And the next LDRH is, this one is 32-bit. We have 8 hexa digit. This move is 32-bit also. So actually, the data and the code, the opcode, the information that will be encoded into the machine code here is including the data, the immediate data. So you see 1, 2 is including in the machine code. So if your immediate value is 32-bit already, so there is no space for you to encode that 32-bit plus the opcode, the opcode for move the information R2 into a 32-bit machine code, because the data is 32-bit already. So that is why in RISC microprocessor, particularly in the ARM microprocessor, because the size of the instruction is 32-bit, all right, already, then you will not be able to have 32-bit immediate value to be encoded to a 32-bit machine code, because that immediate value plus the information here, for example, for the move, you will need to have the code for the move also, right? Plus the immediate value cannot be more than 32-bit, right? So that is why you don't have the instruction to move 32-bit value into a register, right? So that is why. But we can write a single instruction to move an immediate value to a register using the LDR. So for example, we want to move this immediate value into R0 using single instruction in programming. So we can use LDR actually. So what we write in the program is like this: LDR R0 equal 1, 2, 3, 4, 5, 6, 7, 8 hexadecimal. This is allowed, all right? Because the microprocessor, the compiler, and will use the address in the memory to load into R0 instead of the immediate value. So when we, for example, when we use this instruction, let's go to this. Let's we don't know this. We only have this. Instead of move 2 times, we can use LDR here, R2 with this, and all right, we don't have error. Okay, so what the computer do is actually not moving this immediate value to R2, but it will change, the compiler will change this instruction to this, PC plus this 8 to get this 1, 2, 3, 4, 5, 6, 7, 8. And actually the data, this data is predefined in the memory, and the microprocessor get this data from the memory instead of the immediate value. So we can check actually in this location 40C about that. So this is the value actually in 40C. So in the memory, and when we look at the memory 40C, our data is predefined here 1, 2, 3, 4, 5, 6, 7, 8, right? And it will move into R0 using LDR instruction. And this is encoded to only 16-bit instruction or machine code, right? So actually this one is not more than 32-bit. Although the data, we see that here the data is 32-bit, but it is actually predefined in the memory by the compiler. When you compile the code, the compiler will do this automatically, put this value in the memory and use LDR, get the data, put in R2, right? So we can use one instruction to load 32-bit data into memory using LDR. Okay. So that is the use of LDR, which is very interesting. All right. So we go to the next. This is continue from the program flow control just now. where we can use in the programming like this. For example, we have the condition and the flowchart like this, or in C programming, if else statement, for example, right? When we compare in C programming, if A greater than B, we do this, C equal to 1. If not, or if else less than B, or we call it else, C is equal to -1. So in flowchart, in the form of flowchart, it will be uh, drawn like this. If A more than B, so C equal to 1 and done. But else or no, C equal to -1. Right? So this is in C programming or high level language. In assembly language, this is how we do. All right. So we need to assume that A is in R0, B is in R1, and C is in R2. Right. So to know whether A is greater than B or not, or R0 is greater than R1 or not, we use this instruction compare. CMP is compare. Compare R0 R1 means that the microprocessor will check whether R0 is greater than R1 or not, or in other words, it will do subtract R0 minus R1 and see whether the result is positive or negative. If positive means that A is greater than B, or R0 is greater than R1. So in this case, when we compare, and we check the result, if the result is greater, so we have this, right? Greater than, and the number is signed number, so we can use GT or BGT to branch. BGT, branch if greater. All right, B is branch if greater, means that if R0 is greater than R1, we go to this label, right, or branch to this label, next one. So this label is next one. It will skip this line. It will skip this line and go to next one. So what is next one? When greater, yes. When greater, we put C or C equal to 1. So in this case, C is in R2. So we move 1 into R2. So this is C equal to 1. Right? But if not greater, means that A is less than B. So it will not skip this. It will skip this and go to the next line. All right. If the condition is true, it will go to the label. If the condition is false or not true, it will go to the next line, which is this one. So if no, so we move -2 into, -1 into R2, which is this one. All right. And we need to skip this line. All right. We need to skip this line because if we don't skip this line, we will put 1 in R2 after this, right? Because remember, in microprocessor, it will execute line by line. One instruction, after that, another instruction, another instruction, another instruction. It will be executed in sequence. So in our program, we need to skip this one because after we put -1 in R2 or C, we need to end our program. So in this case, we need to go next to. So this is next to the next line. We skip this one. All right. So we use, this is BAL or just B. So this is unconditional branch. This one, always branch or unconditional branch. Means that if you have this B next to, when your microprocessor execute this and execute this, it will always go to next to, go to this line. Okay. So that is how we implement if else statement in assembly language. Now let's see the next one, which is the for loop statement. So how we implement for loop statement in microprocessor in assembly language. So for example, in C code, we want to do something like this. For I equal to 1, and when I less than 10, whenever I less than 10, and we increment I by 1, so means that if I still start from 1, I want A1 equal to this, and we increase I, and we check, A1 is yes, 1 is less than 10, we equal A1 to F0, and we increase I, which is number 2, so A2 equal to this, and again it is still less than 10, I less than 10, we increase I, A3 equal to this, so we will have A1 equal to this, A2 equal to this until A9, right? Because it then 10 is untrue already. All right, we have A1 until A9 is equal to this by using this for loop. So in flowchart, it will be illustrated by this. Yeah, we have I equal to 1, AI equal to this, and we increment I, and we check whether I still less than 10 or not. If still less than 10, we again AI and increment less than 10, AI equal to this, increment until I is equal to 10, then we go exit the loop, right? So this is flowchart, and in assembly language, it should be something like this, right? So we can move 1 to R0. This is this. Yeah, R0 is our I in R0, and we move F0 to R1. All right, means that this is AI F0, and we store in the memory. So this is not this yet, yeah, this is not this yet, just F0 in R1. AI is in the memory. So here R1 we store in the memory pointed by R2, right? This one, and we increment by 1, and we add R0, we add I, yeah, add I by 1, and we compare. Here we compare whether R0 or I is equal to 10 or not, all right, or still less than 10 or not. BLT is less than, branch is less than, right? So if less than 10, we just go back to the loop, this label loop, and yeah, store. So let's see how this is implemented in the memory. Okay, so we have something like this. So let's see, R2 is pointed to location, we have R2 is pointed to location 00000100 in the memory. This is R2. And we have the memory. So this is the memory. And okay, and this is location 100, 101, 102, 103, 104 until we have 109. Let's say 109 is here, 109, 10E. Okay, and we have R0. We have another one. We have R0 and we have R1. We have R1. Okay, so let's see when we execute this program. So we have moved 1 to R0. So our R0 will have 1. Okay, I use maybe I use this color. And we move this value to R1. So our R1 we have this F0 after we execute this instruction. And now we store this R1 go to what is pointed by R2. So what is in R1, which is this, go to the loop, we store the content of R1, which is this, into the memory location pointed by R2. Our R2 is this. So it will go to this location. And the size is byte B, store B, means that F0 will go to this location. We have F0. And remember, this is post index, right? So what you need to do when you have this, you need to update R2 by 1 after you execute this. So R2 will automatically go to, not go to, updated to 101. So this will be 101 after we execute this. And we add R0 to 1. So R0 instead of this, we will have 1. Right? And we compare, is it R0? We compare with 10. So BLT lower than, yes, R0 lower than 10. So we go back to loop. So go back to loop, we do this again. We send what is in R1 to R2, pointed by R2. And our R2, we have 101, which is this. And we send, now we send this value to here, the second location, 101. So we have F0. And again, this is post index. So this is again update this value to 102 plus 1. Yeah. So we have 102 here. And again, here we add 1. So we have R0, we have 2 here. And we compare R0 with 10. Yes, still less than. So we go back to loop. And we will have F0 here. F0 here. If R0 is not 10 yet, until our R0 is 10A, right? Until we have R0 is equal to, no, until R0 is equal to A. This is decimal number. Yeah, decimal number. This is in hexadecimal A. Remember, in the memory, in the register or memory, we use hexadecimal number, but in program, you can use decimal or hexadecimal or binary, up to you. So in this case, it's decimal, but in R0 is hexadecimal, which is A. So we compare, this is A, so it will exit the loop, and at the end, we will get this in our memory as a result. Yeah, this is exactly same with this. Yeah, same with this. So actually, when you write your code in C language, what happened in the microprocessor is actually this. Yeah, the compiler will translate your C program into the equivalent assembly language. Yeah, depend on what microprocessor that you use uh, uh, in your application. Right? In this case, if you use ARM, this will be the uh, assembly code. When you write the code in C like this. All right, so this is the same explanation. I use the same one, starting with a 101. In this case, it's 101, right? Post index. So yes, it's the same. Yeah. Uh, Now let's look at the this one before we have a short break. The while statement. All right. So in C, we can have a code like this. Yeah. While A is not equal to 0, we decrement A, all right, until A equal to 0, and then we exit the loop. So the flowchart can be this, yeah, where we have A equal to 0. If not 0, so we decrement A until A equal to 0, and we exit the loop. So in assembly language, it will be something like this. When our A is in R0, so for example, A is 10. In this case, A is 10, right? So I should update the flowchart a little bit here, where I need to insert A equal to 10 here, right? Later on I will do. So A is 10, and we sub S, remember sub S to update the status flag, start by 1. If not equal to 0, branch if not equal, here is not equal to 0, branch if not equal to 0, look, B and E. So we sub, if not equal to 0, we go back and sub and go back until equal to 0, then we exit the loop, right? So that will be for while statement, which is very useful in our program later on also. For example, we want to create a delay program. So a delay program is very important in microprocessor. For example, if we have something like this, for example, this is our microprocessor. We connect to the LED, and we want to have the interval. For example, we want to send the data, the signal here, to be a clock like this, so that the LED will turn on and off in interval. For example, in 1 second interval, right? 1 second off, 1 second on, and 1 second off again, right? So what we do is to set this output pin to 1 and 0 at 1 second interval. So how do we do that? Is for example, if we write the flowchart or draw the flowchart for that application, so we can have start, we can have on LED, and we can have off LED, and just go back to it again, on off on off on off. But the microprocessor is actually very fast. Yeah, when we on and off here using instruction, one instruction to on the LED, another instruction is to off the LED. So it will run very fast that you cannot see this interval, right? You will not have 1 second interval. So how to get 1 second interval between on and off? So what we do is to have something in between, right? We call it delay. And off LED, and again you have the delay for 1 second until you go back to on again, right? So to write the code for delay here is normally we uh, write the program for the microprocessor to count a number, right? Normally we count from a big number, a very big number. For example, from 1 million, we count, we decrement the number to by 1 until we have 0, right? So if microprocessor count the number here, it will take some time, right? So although the number is 1 million, but because the microprocessor is fast, it will count in less than 1 second maybe. Let's, for example, it will count in 1 second. So we can have the delay 1 second here. So to do that, to do the counting, we will use the while loop, right? So we can set a equal to 1 million, and if a is not equal to 0, so we deduct, reduce by 1 until a equal to 0, and we exit the loop. So for with that, we can have this delay, right? So that is the use of the while loop in programming. Okay, so I think we are at 9:56, almost 10 already. So we have a short break, maybe 10 minutes before we come back.